Hi everyone, welcome to my channel. So in today's video we are going to have a quick recap of the chapter Laws of Motion. Okay, now this video is basically for students like you who have already studied this chapter in class 11. So basically we are going to revise all the important concepts and then we will also solve a few questions. Okay, now this chapter I have divided into two parts. So in today's video I am going to discuss everything except friction. For friction we will have a separate video. Okay, so I am going to discuss all important concepts and we will also solve a few numericals. Okay, so let's start. Now this chapter is basically study of force. Okay, now the concept of this force was first given by Aristotle. Now Aristotle, he proposed, actually this law of inertia was initially given by Aristotle. Now according to Aristotle, he said that force is something which is necessary for motion, for maintaining motion. Okay, now to a common man it appears to be a correct, but you know that this is not true. Force is not required to maintain motion. Force is actually is required to initiate motion or to change the state of motion. That means, like suppose this duster is in state of rest. Now in order to move this duster you need to apply some force, and if this duster is in a state of motion, then to bring it to state of rest you need to apply some force. Okay, so that the concept given by Aristotle on force, that was a wrong concept and that was later rectified by Newton. Okay, now this force basically is something which changes the state of a body from state of rest to state of motion, or from state of motion to state of rest. Or if it is state of motion, let's say it is moving with a constant velocity, then if we apply some force, then its velocity may increase or decrease depending upon direction of application of force. Okay, now those things we will study later on, but this is the basic idea about force. Now this force, it is basically of two types. Okay, contact force and non-contact force. Okay, now in this chapter basically we are going to study about this contact force. Okay, there are non-contact forces also, like gravitational force, okay, then electrostatic force, magnetic force, so that we will study later on. Okay, gravitational force is there in later part of the first year syllabus, and electrostatic force and magnetic force, it is there in second year, okay, class 12 syllabus. Okay, so those are non-contact forces, but basically in this chapter we are going to study about contact forces. Contact forces means the forces which comes in contact with the body, okay, and then it changes the state of the body. Okay, so that kind of force is called contact force. Okay, like push or pull, all those forces are contact forces. So these are the two types of force, contact forces and non-contact forces. Okay, now next let us move on to the laws of motion. Now, before we go further, like one important thing is, like probably you are watching me on a mobile or a laptop, so it will be better if you are sitting properly and having a notebook and a pen and writing things as I am saying, and based on your understanding, of course. Okay, so that will be better. Achha, now let's proceed further. Now next comes the laws of motion as a chapter. Okay, now basically we have these three laws of motion. Okay, now these laws of motion were stated by Isaac Newton. So first law, it is the law of inertia. Second law, this connects force and momentum by the relation F is equal to F proportional to dP by dt. Okay, F is the force, P is the momentum, so force is directly proportional to rate of changing momentum. And third law, it says that action is equal to negative of reaction. Okay, now we will see each and every law in detail. Okay, because this chapter is laws of motion, so we need to understand the three laws. Okay, now first law, that is the law of inertia. That is, if external force is zero, this is F external. Okay, if external force is 0, then the state of the body is not going to change. That is, if the body is in state of rest, it will continue in the state of rest. If the body is in state of motion, it will continue in the state of motion. Okay. Now this F external is equal to 0. This implies the body is in equilibrium. The body is in equilibrium. Okay. Now equilibrium implies in this chapter. See, we have not studied rotational motion, so we are studying about the concept of force. So that means we are studying about translation. So that means if the body is in equilibrium, if the net force is 0, okay, and the body is in equilibrium, then we can say that there is no translatory motion if the body is in rest. Okay, and if the body is in motion, the body will move in translatory motion without any change in direction. Okay, actually, see, these three laws are interrelated. Okay, so if you go a bit in deep, then you will see that these laws, actually the three laws are actually a single law. They are interrelated and they are related to this second law. I can say that the second law is the most fundamental law. Okay, so first law, the law of inertia, says that if there is no force, then the body will stay in the same state. There will not be any change of state. Okay, this change of state is not that thermodynamical state. Okay, this is state of rest or state of motion. Okay, so this is law of inertia. Now second law is a bit complicated, means it has some deeper meaning. Second law says that force is proportional to dV by dt. Okay, now we need to understand the meaning of each and every term involved here. First of all, this force F, this is the external force. This is the external force. It is not an internal force. Okay, and this P, this is momentum. So dP represents the change in momentum of the body on which this external force acts. Okay, now this can be written as F is equal to dP by dt. Okay, now here I have taken that the proportionality constant, the value of this proportionality constant is 1. You know why it is. Okay, now F is equal to dP by dt. So I can write this as F is equal to d by dt of mv. Momentum is mass times velocity, correct? Okay, so now see, this momentum involves two terms, mass and velocity. So I can write this as F is equal to m pv by dt plus v dm by dt. Okay, so here dv by dt represents the rate of change in velocity and dm by dt represents the rate of change in mass. Okay, so this is the general expression for force. This is the general expression for force. Now there are two possibilities. Okay, two possibilities. One possibility is if mass is constant. Now if mass is constant, then dm by dt will be equal to how much? It will be equal to 0. So this term will vanish. So F is equal to m dv by dt. Okay, so F is equal to m dv by dt, or I will write it as F is equal to m into a, because dv by dt is acceleration. So this F is equal to ma is valid only when mass is a constant. Okay, mass is a constant. Now in case velocity is constant, so in that case I can write v is equal to constant. Now if velocity is constant, dv by dt will be equal to 0. dv by dt equal to 0 implies this term is 0. So F will be equal to v dm by dt. Okay, F is equal to v dm by dt, where dm by dt is the rate of change in mass. Okay, now let us solve one question based on this concept. So suppose this is a frictionless surface. This is a block of mass 2 kg. Okay, so this block of mass 2 kg is placed on a frictionless surface, and this is a horizontal pipe. Okay, and through this pipe, suppose water is coming out. Okay, and it is hitting this block. Okay, so the water which is coming out it has a velocity of say 2 meter per second, and the amount of water that is striking this block, it is per unit time, suppose it is 3 kg per second, 3 kg per second, okay, and you are asked to find the initial acceleration of this block, because if the water strikes this block, okay, then the block is going to move, okay. So what will be the initial acceleration? So see here, so you see, if you remember this equation, F is equal to ma, and if you try using this expression in this particular question, then you will not get a solution, because see, there is no idea about acceleration. In fact, it is given that this water is striking this block with a constant velocity. Okay, if you think about that velocity is constant, then acceleration will be 0, and acceleration 0 implies force equal to 0. But that is not true, because we know that if water is striking this block, obviously this block is going to experience a force and it is going to move in this direction. Correct? So that is why this expression comes into rescue. This F is equal to V dm by dt. So here, see, this velocity is 2 meter per second. Okay, now initial acceleration is asked, direction is not asked, so obviously we need the magnitude of the acceleration. So for that we first find the force. So force equal to, this velocity is this quantity 2 meter per second, okay, and then dm by dt is 3 kg per second, so into 3 kg per second, okay. So this is 3 to the 6, so F is equal to 6 Newton, okay, means this is kg meter per second square, but that is equal to Newton, so 6 Newton is the force. So that means this block is acted upon by a force of 6 Newton. So what will be the initial acceleration? A is equal to force by mass, correct? So this is how much? This is 6 divided by 2, so that is equal to 3 meter per second square. So that is the initial acceleration of the block. Acha. Another important thing is, see, when I write F is equal to dt by dt, okay, now if mass is constant, this becomes F is equal to m dv by dt, okay. So this force is equal to mass times rate of changing velocity, Now see, velocity, suppose velocity is, it is in this direction, this is the direction of the velocity, okay, and this is the direction of force, okay. Theta is the angle between force and velocity, okay. So I can resolve this velocity as this component v cos theta, this is theta, this is v, so this will be v cos theta, and this will be v sin theta. So this v sin theta is, I can call this as v perpendicular, because this component of velocity is perpendicular to force, and this v cos theta, I will call it as v parallel, because this is the component of velocity which is parallel to force, okay. So this force can change only this component of velocity. Force can change the component of velocity which is parallel to the force. It cannot change the component of velocity which is perpendicular to the force. So that means this v sin theta, there is no change, okay, no change in this component, but v parallel, this component changes, okay. So you must write it that component of velocity which is parallel to the force, it changes, means if the force is in the direction of velocity, obviously in this case velocity and force, they are in the same direction, so this velocity is going to increase, okay. If force and velocity, they are in opposite direction, then velocity is going to decrease, but the component of velocity which is perpendicular to force, it is not going to change, okay. Now you will say that sir is saying this, but we don't agree, okay. You want a proof, because you don't, why I am saying that this component of velocity perpendicular to the force, it is not changing. Why it is not changing? Okay, you want a practical proof. Okay, so let us see a practical proof. We have studied projectile motion. Okay, so this is horizontal direction x-axis, this is vertical direction y-axis. Okay, now a projectile is projected with velocity u at an angle theta with the horizontal. So this is the trajectory. Okay, now see, at this particular point, if I draw a tangent, this is the direction of the velocity. In the trajectory, at any point, if you draw a tangent, the tangent will give you the direction of velocity, correct? Achha. Now, this is the horizontal component. Okay, I will call this as, let us say, suppose this angle is alpha, so this will be V cos alpha, and this will be V sin alpha. Okay, now what is the direction of the gravitational force? Gravitational force will act in vertical downward direction. Okay, so this is the direction of the gravitational force. So see here, gravitational force is anti-parallel to V sin theta. So that means this gravitational force is going to affect this component of velocity. And how it is going to affect? As the projectile moves from this point to this point, this is the highest point, this V sin theta will keep on, V sin alpha will keep on decreasing. Why? Because force is in the downward direction. Now after this point, what will happen? This velocity vector will move in the downward direction and force is also in the downward direction. So the velocity will start increasing. Okay, but this component of velocity, this velocity is perpendicular to the force, perpendicular to the gravitational force. So there will not be any change. There is not any change in this component of velocity. And we understand this from point of view of gravitation, that since gravitational force acts in the vertical downward direction, there is no horizontal force. We say that horizontal component of velocity is a constant. Correct? So this is clear now that force can change only that component of velocity which is parallel or anti-parallel to the direction of force. Okay, component of velocity which is perpendicular to force will remain invariant. It will not change. Okay. Achha, now, so from second law we have got this expression F is equal to ma. This is for obviously for constant mass, when mass is constant. Okay, now here this is concept is very important, that this force F, this is external force. Okay, this is external force. Okay, now when multiple forces are involved, okay, suppose external number of forces are involved, external forces are involved, internal forces are also involved. Okay, so in such cases, this expression F will only represent external force, no internal force, no internal force. Internal force is never taken into account. Okay, another important thing is this F and A. If you apply a force, you get this acceleration. So these are instantaneous values. This F and A are instantaneous values. The value of acceleration does not depend on the previous history. Like just a few moments back, what is the acceleration? It is not going to affect the present acceleration, because the present acceleration of the body depends on the present force which is acting on the body. Okay, so this is another very important concept. And the other important thing is this expression is valid for number one, point mass, okay, or it is valid for rigid bodies. Only for such cases we can apply this law, F is equal to ma. Okay, so I hope this picture about surrounding this expression, when we have F equal to ma, when we don't have F equal to ma, what is this F, what is this A, all those things are clear. Okay, so let's proceed. So next topic is impulse, denoted by the symbol J, and in some books it is represented by the symbol I. Okay, I will prefer using J. Okay, so impulse, basically it is impact of force for a short interval of time. That is the definition. But mathematically, how to represent it? See, J impulse is equal to integral F dt. Okay, so this is from T1 to T2. So F is the force acting in a short interval of time, dt. Okay, now from second law we have F is equal to dp by dt. So this, if we substitute over here, we get J is equal to integral P initial, P final, dp. So that is equal to P final minus P initial. So this is the relation between impulse and change in momentum. Impulse and change in momentum. Okay, and this is also called impulse momentum theorem. Okay, impulse momentum theorem. Impulse momentum theorem. Okay, now where it is used? Like suppose you have a ball hitting a vertical wall. Okay, now suppose this is a vertical wall, this is fixed rigid wall, this wall is not going to move. The ball comes like this and it bounces and goes like this. Okay, now suppose this angle is theta. So suppose we are taking elastic collision. Okay, in collision we will study this, that for elastic collision these two angles will be equal. Okay, angle of, we can say that this is angle of incidence, this is angle of reflection in the language of optics. Okay, so this ball was going in this direction. So this is the direction of the initial momentum, P initial. Okay, this angle is theta, so this angle is also theta. So this is P initial. So this is P initial cos theta. This is P initial sin theta. Okay. Now when it bounces, it goes in this direction. So this is P final. So this is theta. So this is P final cos theta, and this is P final sin theta. Okay. Now if you find the change in momentum, so suppose this is your x-axis, this is your y-axis. So change in momentum along x-axis, it will be this is P final cos theta. So final momentum minus initial momentum. So if I take this direction as positive direction, this will be negative direction. So this will be minus PF cos theta. Okay, minus PI cos theta. Okay. Similarly, delta PY, this is y-axis. So both the final momentum and initial momentum, they are in the downward direction. So final momentum is minus PF sin theta minus of minus PI sin theta. Okay, so this is the change in momentum along x-axis, this is the change in momentum along y-axis. Okay, now if in the question it is given that mass and velocity before and after collision they are same, so in that case this change in momentum along y-axis, it will be 0, and finally we will get momentum change along x-axis only. Okay, so this is how you can calculate the change in momentum, and this change in momentum is equal to the impulse imparted to the ball by the wall. Okay, because impulse is equal to change in momentum. Okay, so for such kind of concept you can use this relation, that is the impulse momentum theorem. Okay, now let us check a few graph based concept. Like suppose you have a graph between momentum and time. Momentum and time. Okay, and suppose the graph is like this. Okay, now if you find the slope at a particular point, suppose at this point, particular point, if you find the slope, then you have to draw a tangent. So this theta, tan theta will give you the slope at this particular point. Okay, but what is that slope called? So slope at this particular point means you are finding dq by dt. But what is that? That is equal to, that is the force, and that is equal to tan theta. So if you have a momentum time graph, you are finding the slope at a particular point. That means you are finding the force acting at that particular time. Okay, so this is slope of momentum time graph gives force. Okay, now suppose you have force time graph, force and time, and the graph is like this. Okay, this is the graph. Okay, so see area of this graph, because see impulse, it is equal to T1 to T2 F dt, that we have already seen. Now what is this? Integration f dt, that is the area under the graph, ft graph. So that means if you find the area, okay, if you find the area, that means you are calculating the impulse, or you are calculating the change in momentum, because impulse equal to change in momentum. So if the force time graph is given and if you are finding the area, if you are finding the area, then the area will give the impulse, okay, or the change in momentum. But one thing you have to keep in mind, that suppose for this half, the area will be positive, okay. For this half, the area will be negative, okay. So that also you need to consider, because see, impulse is a vector quantity, force is a vector quantity, impulse equal to change in momentum, momentum is also a vector quantity. So when you are calculating this part, area of this part, it should be considered as a negative area, okay. So this is few important concepts based on graphs, okay. Now next, moving to the topic of rocket propulsion. Rocket propulsion, okay. Now suppose this is a rocket, okay, and it is ejecting gas, fuel is burning out, and the fuel is burning at rate dm by dt, and the gas which is coming out, its velocity is v relative. V relative means velocity of this gas, ejected gas, relative to the rocket, okay. And the rocket is moving in the forward direction, okay, it is going in the upward direction, okay. Now suppose the rocket is moving with acceleration a, okay, acceleration a in the upward direction, okay. In that case, what you need to do, m is the mass, instantaneous mass into acceleration. This is equal to, see, this velocity is imparting, this velocity is relative to the rocket, so this constant velocity, so the mass that is burning is dm by dt, so the force that is exerted on the rocket, it is v relative dm by dt. This is the force acting in the upward direction, this is producing the thrust on the rocket, okay, and minus mg, why minus mg? Because weight of the rocket is acting in the downward direction, so this is the net force, so this is the equation, okay. This is the case when it is accelerating in the upward direction, a is the acceleration, okay. Now if it is moving constant velocity, if it is moving with constant velocity, so in that case a will be equal to 0. So if a is equal to 0, that means this quantity becomes 0. So we have v relative dm by dt is equal to mg. Okay. So based on given information in the question, you can simplify this equation. Okay. So if acceleration is there, then you have to use this mass into the acceleration. Given acceleration is equal to the net force. If the acceleration is 0, that means the rocket is moving with the constant velocity. So in that case, the acceleration will be equal to 0. So this term vanishes. So we have this v relative dm by dt minus mg is equal to 0. So this mg goes to the other side. So we have this expression. Okay. So this is for rocket propulsion. Okay. Achha, next, moving to third law of motion, Newton's third law of motion. Okay. Now suppose we have two objects in contact. Okay. Or say the objects are placed like this. These are the two objects. Okay. So this is suppose object A, this is object B. Then force exerted by object A on object B, this is FBA. Suppose this is the force exerted on B by A. Okay. Now force exerted on A by B, it is FAB. Okay. So this is the mutual force between A and B. Okay. Now the third law, Newton's third law, it says that this FAB is equal to minus FBA. That is, if I take this force as action, then this implies this is the reaction. So that means for every action there is an equal and opposite reaction. Okay. Action and reaction, they are always equal in magnitude but opposite in direction. See, one force is acting in the downward direction, another force is acting in the upward direction. So action and reaction, they are in opposite direction. they are always equal in magnitude. And the other important thing is action and reaction will always take place on different bodies. See, action, suppose if I take the action of A on B, then reaction is on A. Means if the action is taking place on B, reaction is taking place on A. Action and reaction will never take place on the same body. Okay, so action and reaction, they always occur in pairs. Okay, they will be always be in pairs, and they will always take place on different bodies, never on same body. Okay, this is a very important concept. Okay, so this is all about third law, Newton's third law. Now let us consider the motion of man in a lift. Motion of man in a lift. Okay, now suppose this is a lift and this is a man, and the man is standing on a weighing machine inside the lift, and the lift is stationary or it is moving with constant velocity. Okay, so lift is either it is at rest or it is moving with constant velocity. Okay, so for either of the two cases, it implies acceleration of the system is 0. Correct? Okay. Now, see, what is the force exerted by the man on the weighing machine? That is mg. And what is the force exerted by the weighing machine on the man? That is normal reaction. Okay. Now, it is this normal reaction which appears as the reading which we see in the weighing machine. Okay, this is our weight. Okay, so the reading shown by the this weighing machine is the normal reaction. Okay, and under this condition, see, velocity is 0, that means acceleration is 0, that means total net force of the system is 0. So net upward force equal to net downward force. So I will write N equal to mg. Okay, now here this N is the apparent weight. Apparent weight. The apparent weight means observed weight. Okay, and mg, what is mg? This is the actual weight. This is the actual weight. So when the lift is at rest or when it is moving with constant velocity, apparent weight and actual weight will be same. Okay. Now what will happen if the lift starts accelerating in the downward direction? So this same man standing on the weighing machine, and the lift is accelerating in the downward direction. Okay. Now what will happen? See, this is the normal reaction. This is mg, but now the system is accelerating in the downward direction. So since the system is accelerating in the downward direction, so if you observe this man, there are two forces, N acting in the upward direction, mg acting in the downward direction. So net force is in the downward direction. Why? Because acceleration is in the downward direction. So net force will be force having greater magnitude mg, downward force minus N is equal to m into A. Okay, so why I have written like this? Because acceleration is in the downward direction. So this force will be greater than this force, and that is equal to the net force. Okay, so this is N is equal to m g minus A. So that means N will be less than mg. N will be less than mg. So in this case, apparent weight will be less than the actual weight. So man will see that his weight has reduced. If the lift is accelerating in the downward direction, he will experience as if the weight has reduced. Okay, and in case this cable snaps, the cable of the lift snaps, so this A becomes G and N becomes 0, so the person will experience weightlessness. Okay, so the weight decreases as the lift moves in the downward direction. So what will happen if the lift moves in the upward direction? If it accelerates in the upward direction, so just by observing this, we can say that obviously he will see that his weight has increased. Apparent weight will be greater than the actual weight. Okay, now let us see this mathematically. So if this is the lift and lift is accelerating upward, so this is N, this is mg. So see here the acceleration is in the upward direction, so this force will be greater than this force. Okay, so we have N minus mg is equal to ma. So N is equal to mg plus A. So obviously here N is greater than mg. Normal reaction is greater than the weight. So he will experience as if the weight has increased. Okay. Now this same concept can be applied to this monkey rope problem. Suppose this is the monkey, this is the tail. So this monkey is holding this rope which is attached to some rigid support. So if the monkey is moving upward with acceleration A, okay, so this is the rope, so this tension T, this is mg is acting in the downward direction. If the monkey is accelerating upward, so in that case T minus mg will be equal to ma. If it is accelerating upward, that means upward force is greater than downward force. So T is greater than mg. So net force is upward force minus downward force. Both the forces are acting in opposite direction. So this is T is equal to m g plus a. So that means if the monkey is moving in the upward direction with acceleration a, in that case tension in the rope will be m g plus a. Similarly, if the monkey is coming down, obviously I can say that tension will be equal to m g minus a. So obviously in this case tension will be greater. So if the monkey is moving in the upward direction, so there will be chance of breakage. Like if problem is asked based on like in which situation the string breaks, okay, if the breaking stress is given, okay. So in that case the common sense we have to apply is like when the monkey is ascending, when the monkey is moving in the upward direction, in that case tension will be maximum, okay, tension will be minimum when the monkey is accelerating in the downward direction from the rope, okay. So next, moving to the concept of contact force. Okay. Now, suppose you have two blocks in contact. Okay. Now, this smaller block of mass m, bigger block of mass capital M. There is a smaller, this capital M. So, smaller block is acted upon by force F. So this force is acting on smaller block. So assuming both the blocks are moving with same acceleration. Okay. Now this smaller block will exert a force on bigger block. Suppose that is this force F. Okay. Now this is the internal force. Now internal force is like action. This force is action acting on capital M. So now it will produce a reaction. So that reaction force will be small f acting on small m. Both are F because action and reaction they are always equal in magnitude, opposite in direction. So if I draw the free body diagram for this mass separately, so this is M. So in this direction we have force capital F, this direction we have force small f, which is moving with acceleration. So for this mass I can write F minus F is equal to M into A. Correct? Achha. What about this? For this bigger mass, now it is acted upon by this force, contact force. There is no external force acting on this. Okay. So this is moving with acceleration A. So this F is equal to M into A. Correct? So this F, if we substitute over here, we get A is equal to F divided by M plus M. And if you substitute this A over here, so we get F is equal to M F divided by M plus M. Okay. So this is the expression for the contact force that is developed between the two masses. Okay. So this is how you have to calculate the contact force. The same concept can be applied for calculating the this contact force between three masses. Okay. This underlying principle remains same. Okay. Now let us use this concept, similar concept, to calculate tension in a string. Okay, tension in a string, like in horizontal case. This is mass small m. So this is string, and this is another mass capital M. Now this is moved in the horizontal direction by applying force F. This is suppose acting in the horizontal direction. Now this force is acting on this mass, and these two masses are connected by a string. Now again, this string in this chapter, this string, unless it is stated anything about the string is assumed to be massless. It is assumed to be inextensible. Okay. Acha. Now, so at this point tension will be in this direction. At this point tension will be in this direction. Both the tensions will be same, provided it is ideal string, that is massless, inextensible. Okay. So this tension is responsible for motion of this mass. So this is acceleration A. So this is T is equal to ma. Force equal to mass into acceleration. For this Suppose assuming both the masses are moving with same acceleration. So for this force F is acting in this direction, tension is acting in this direction. So F minus T is equal to m into A. Okay, so if I substitute this value of P over here, I get acceleration equal to force divided by m plus m. Okay, now you need not calculate this thing in such a lengthy manner, because the acceleration is equal to force by mass. Acceleration is the same acceleration, both are moving with the same. Under the condition if these two masses are moving in the same acceleration, then only you can use this formula, this shortcut technique, that acceleration is equal to force divided by mass. Force divided by total mass. Okay, and this acceleration, if you substitute over here, you get the value of the tension. T is equal to m F divided by m plus m. Okay, so this is how you can calculate the tension. Okay, now let us see this pulley mass system. Pulley mass system. So you have this pulley fixed to a rigid support, and this is string passing over the pulley. This is mass m1, this is mass m2. Okay, now here in this chapter there are certain assumptions, like for example I told you about this string. This string is going to be inextensible, massless. Then this pulley is also going to be massless, it is not going to have any mass. We will assume that it is not having any mass. If it is having mass, what will happen? Then those things we will learn in rotational motion, because their moment of inertia will also come into play. So in this chapter basically pulley won't have any mass and there will not be any friction. Pulley is assumed to be smooth, so there will not be any friction here. Okay, ideal case. So in that case both side tension will be same. So here this is tension T, here this is tension T. So this is M2G, this is M1G. Okay, now assuming this M2 is greater than M1, okay, so that means this is coming downwards, this is going upward. Okay, so if you are asked to write the equation for acceleration, then it is acceleration is net force divided by net mass. So net force, see, M2G is pulling in this direction, M1G is pulling in this direction. It appears that both are acting in a downward direction, but actually they are acting in opposite direction, because see, M1G is opposing this force M2G. So net force is M2G minus M1G. This is the net force, and this force is acting on which mass? Total mass of the system, M1 plus M2. M1 plus M2. So A is equal to M2 minus M1 into G divided by M1 plus M2. This is the expression for acceleration. Okay. Now, if tension, you need to find tension. So if you substitute this value over any of one equation, suppose if I frame this equation over this side, so this is T minus M1G is equal to M1 into A. If you substitute that A over here, we can get the value of T. But it is better if you remember this equation. Tension is equal to twice M1 M2G divided by M1 plus M2. This is the expression for tension. Okay, and if this is T, this is T, tension at this point, if it is asked, it will be 2T. It will be 2T. Okay, why 2T? Because see, suppose I don't know what is this tension. Okay, and I need to find it. So for this pulley, see, this side tension is T, this side tension is T, and this side I don't know. Suppose this is Tx. Okay, so this is Tx minus 2T, Tx minus 2T, it is equal to 0, it is going to be equal to 0. Why? Because this pulley is massless, so net force on this will be equal to 0. Force is mass into acceleration, mass is 0 means force is 0. So this Tx, what is Tx minus 2T equal to 0? So Tx equal to how much? 2T. So this force will be, tension will be equal to 2T, therefore this is 2T. Okay. So this is the simple case when we have only single pulley. Okay. Now what will happen if we have more than one pulley? Then what will you do? So suppose we have a situation like this. This is one pulley. This is mass. This is another pulley. This is mass. Suppose this is M1. This is M2. Okay. So now see, this is a single string. This is single string. So this is tension T, this is tension T, this is tension T. So this is twice T. So if this is T, this is twice T. Okay. Now so here see, tension is different. Okay. Acceleration is also going to be different. Okay. So tension is different, acceleration is different. So we have more than required number of unknowns. So if we have more than required number of unknowns, then we require more equations to simplify them. Then it becomes a bit complicated. Now to simplify such situations, what you need to do is, see, first of all, one simplification we have done is we have not written T1, T2. We are sure that if this tension is T, this tension is twice T. Okay. Another thing is, see, for a pulley mass system, multiple pulley mass system, the product of tension into acceleration, this product will be a constant. This product is going to be a constant. So suppose this is M1G. Now this is M1, so this will be M1G. This is M2G. Now if I take this, suppose it is moving in the upward direction with acceleration A. This is moving with downward direction. So if this acceleration is A, so product of tension into acceleration, I told it is a constant. So if this is T, this is A. So that means if this is 2T, what will be the acceleration? It will be A by 2. Because see, if I multiply this, it is TA. This is 2T. 2T into A by 2 will be TA. That product should remain a constant for the system. Okay. So now we have the relation between tension. We also have a relation between acceleration. So now it is much easier to solve because there are only two unknowns, T and A, and we can write two equations and we can simplify it. Okay. So this is one very important concept, that for a multiple pulley mass system, the product of tension into acceleration is going to be a constant. Okay. So these were few of the concepts related to the chapter laws of motion, excluding the friction part. Okay. Now based on this lecture, I am going to give you a practice sheet. Okay, which is basically a collection of few questions. You try out those questions, and in case of any clarification, you can contact me. Okay, we can discuss those questions if you are having some difficulties. So with this, I end this video. Hope this video is beneficial to you. My best wishes to you.